Alright, so hopefully you're just fresh off of this different video that describes how we can essentially adjust our bases in accordance to rotation essentially of our apparatus by some degree theta. So if we say have some apparatus that's measuring the 0 and 180 degree directions, right, up and down, north, south, if we rotate it by say 60 degrees, right, how do you represent, what's the bases that we're going to be using for this new rotated apparatus? How are we going to represent the possibilities of spin for that given particle, say an electron? And so actually let's investigate and walk through an example of this with say the 60-degree rotation that we just mentioned, right? So let's say we first took some little electron, some little guy, Bob, right? And we took an electron, we say, hey, we're going to pass you through this apparatus, and based off of the apparatus you are deflected in such a way such that we know that your spin is directed in the northward direction. Right, all right, so Bob's spin is in the northward direction towards 0 degrees, if you want to kind of put it in terms of degrees right here, right? And we're going to avoid calling it spin up in the specific case just because depending on how you tilt your head or tilt your screen or just anything where your frame of reference up and down can be a little bit of a strange term to use. Now, let's go back to what we said about our 60-degree rotation. Now, 60-degree rotation for the apparatus becomes theta. So theta here equals 60 degrees. Now, as you may recall, when we want to say change the rotation, actually I take that back, rotate a given apparatus by some degree, the resultant bases that we're going to be using is going to look something along the lines of cosine of theta over 2 and negative sine theta over 2, and that is our first vector. And our second one being sine of theta over 2 and cosine of theta over 2. Right, I'm running a little bit short on the space right here, so let me shrink that down and give us a little bit more room. Alright, so with this relationship, and now that we have theta, we can determine the bases for which we're going to be measuring the spin of this particle Bob in with this new apparatus, the one that has been rotated, right? And so to do so, let's go through the motions of it. So now we know that theta is equal to 60 degrees. And so with that in mind, what we can fundamentally do is take theta, right, 60 degrees, and divide that by 2. We'll just go ahead and do that, and that becomes 30 degrees. And once we do that, we'll just kind of keep that in the back of our mind, right? And fundamentally move on from there. Now, with that in mind, cosine of 30 degrees, which becomes our first kind of element in the set, cosine of 30 degrees fundamentally becomes root 3 over 2, right? And so if I was to write them in parallel with one another, so we can see them both going on at the same time, right? So cosine of 30 is equivalent to root 3 over 2, right? And then negative sine of 30 degrees becomes negative 1/2. And again, following the same relationship that we have here, we have sine of 30 degrees, right? And that is equal to 1/2, and I'm just writing, the angles out here, and then writing the actual values on the bottom, and then we have cosine of 30 degrees becoming root 3 over 2, again positive, right? And so this is the basis we're going to be measuring our given spin direction in, and so this right here is something that we have to remember. Now, we know that our spin, this measured value for spin that we got, right, fundamentally was given as spin in the northward direction. In other words, the spin that we measured was 1, 0, right? And that's the vector, the linear combination fundamentally representing it, or we can just say that was the state vector representing the spin direction that we measured. Now we want to express this spin as a linear combination of our new basis vectors. In order to get these coordinates, the coefficients for the linear combination, we will have to go through with something you may or may not recall, which was essentially taking a matrix composed of the bras of our new bases that we established. So in this case, keep in mind, bras kind of go in the horizontal direction, right? So our first one is root 3 over 2 and negative 1 over 2, and our second one is 1 over 2 and root 3 over 2. And we multiply that by the ket composed of our initial kind of value, the one that we measured, right? And when multiplied out, keep in mind, this gives us, right, the coefficients that we're looking for in the order of the basis vectors that we have listed right over here. And so when multiplied out, you end up with something along the lines of root 3 over 2 and 1 over 2, right? And so, taking this newfound information, there are several ways to go. And the first one being that we are going to write out a full formula just to illustrate precisely what we have here. Shrink that. Right, so we said that 1 over 1, 0, right, can be represented as some linear combination of our basis vectors, this new set of basis vectors that we have determined. Right, something, right, over here, right, with some coefficient, plus some coefficient, and 1/2, and root 3 over 2. Right, and as we mentioned earlier, this is simply put how you find the coefficients, kind of shortcut method, and I won't go into detail on precisely how that is, and that was something we did cover in the past. And fundamentally, we do know that the coefficient here is root 3 over 2, and the coefficient here is 1 over 2. And now, in the context of quantum computing and measuring spin, fundamentally, what this coefficient represents is, the probability amplitude, in a sense, which is saying that this here is like the 60-degree direction, right? Measuring spin in 60 degrees, and this here is its partner in the opposite direction. So this is essentially like a saying that the probability of measuring spin for the same little particle bob in the 60-degree direction after we've rotated that apparatus, or after we send bob through our initial apparatus knowing it has spin in the northward direction, and we send it through a second one that's been rotated by 60 degrees, we know that the probability of measuring bob's spin at 60 degrees is equal to root 3 over 2 squared, which is equal to 3/4, which is equal to 75%. So there's a 75% chance that when we measure the spin of bob with respect to essentially this new apparatus, our resultant will be in the 60-degree direction. We'll have spin, and the result of it tell us that spin, bob spins in the 60-degree direction. Alright, so that's basically just a quick walkthrough of one way of just rotating the apparatus by 60 degrees and illustrating the formula that we established earlier regarding how to kind of move between the bases in association to a spin direction, right? And of course, determining and relating that to determine the probability of getting some degree, some direction within this given basis and within the direction that we're measuring it in. As always, if you have any questions, please do not hesitate to visit the qmunitytech website. And as always, stay curious and keep on learning.